Okay, this is the study guide for the 5.1 to 5.4 quiz. So we're trying to find the rate of change here, which is the same as asking what is the slope. You can just count using the chart, but I like to use the slope formula too. So the grade changes by 2 every time the hours change by 1. So you could say for each hour you study, you get 2 points higher of a grade, or your grade goes up 2 points for every hour you study. In the second table, the y column goes up by 75. But the x column, like that first column, goes up by 3. So here it's 75 over 3. That reduces to 25 over 1. Or you could use the slope formula, which is the same thing. I'm still like doing the change in y over change in x. It's still a change of 25 over 1. So the car travels 75 meters every 3 seconds. But you could just say the car is traveling 25 meters per second. So that's what the scenario is described here. And here you can see if you divide the units, that's where you get the meters per second from, or you can just kind of use common sense. For the next one, we're trying to find the slope. Just like we calculated before, we can use that change in y over change in x formula. It doesn't matter which way you subtract them. And here I'm going to do the first minus the second, but I got to be consistent. In the denominator, I got to do the first minus the second. The change is 2 over 2. That reduces to 1 over 1. You could say your slope is just 1. You can write it as a fraction if you want. It's a whole number. There's no need to write it as a fraction, though, but it's not wrong if you do it that way. Here I'm going to do second minus first. But again, I'm just doing change in y over change in x. What is important is that you do the change in y on top, change in x on the bottom. And this one is also a slope of 1. Just to plot and check that this is a slope of 1, you can do this graphically. Plot the 2 points, and you can check the slope that way. Every time I go up 1, I go over 1. Graphing just is a little, there's nothing wrong with it. It just takes a little more time, so it's good to know that slope formula. Here I'm going to find the slope between these 2 points. Notice that my change in x is 0, so that's going to be a slope of undefined. And whenever you have an undefined slope, you should remember that happens when you have a vertical line. So you can still graph it, but it's going to be a vertical line when you graph it. Because the x here, it was 6 regardless of what the y value was. For number 6, this time the change in y was 0, and it doesn't matter what order you subtract it in. It's still like 0 over 10 or 0 over negative 10. Either way, the slope is 0, and you should remember that the slope of 0 is a slope of a horizontal line. For number 7, we're looking for direct variations. And k is that constant of variation, or sometimes we call it a constant of proportionality. And so that k in this case is 3. And here's how you can confirm that it's a direct variation. If you made a table between the x and y values, the x and y values are directly proportional. Also, the graph goes through the origin, or you could say instead of it goes through the origin, you could say the y-intercept is 0. But that's what a direct variation is. It's directly proportional, or it's a linear equation that goes through the origin, or a linear equation that has a y-intercept of 0. For number 8, it looks like it might not be a direct variation because we see like those plus signs. That usually is a little key that you're not going to have a direct variation. But since there's a 3 on each side, when you subtract 3 on each side, they sort of cancel each other out. And so we want to get this as y equals kx, so we want to solve for y here. Get y by itself, you divide by 8 on each side, and so you get 5/8 x equals y, or y equals 5/8 x. So your k value is 5 over 8, or you could write it as a decimal right here by putting that in your calculator and calculating that. But this is going to be a direct variation. Number 9, I'm going to get y by itself. Because if we can get it in the form of y equals kx, if it's a direct variation, you can solve for the k. So I'm going to move the negative 3x over by adding it to both sides. I got to divide by the coefficient of y to get y by itself. And once I do that, though, I don't get y equals kx. I get like a y equals kx plus some stuff left over. So since the stuff left over, or the y-intercept, is not 0, this is not going to be a direct variation. This does not go through the origin. If you did try to graph this, the y-intercept would be just some negative number. Since it doesn't go through the origin, the y and the x are not proportional. They are not direct variations. Here I'm trying to find the slope and the y-intercept of each graph. Since this equation is in slope-intercept form, the slope is the coefficient of x, And then the y-intercept is that number that's off by itself. I could say the slope is 1/5. You could put it as a decimal as well. The slope can be 1/5 there if you want to leave it as a fraction. The y-intercept is 3. We don't have to graph it, but just so you know physically what each of those things mean. The y-intercept is where it hits the y-axis. The slope is going up 1/5. That's what the graph of the equation looks like. So it's good to get a good physical understanding of what those are. Slope, where it hits the y-axis. The y-intercept is where it hits the y-axis. The slope going up 1/5. Number 11, again, we just want to figure out what the slope and the y-intercept are. So I like to do that by putting in slope-intercept form, but this one's not in slope-intercept form. So to get in slope-intercept form, you get the y by itself. So we move the 3x to the other side. We divide by the coefficient of y. Now the y is by itself, so we get y equals negative 3/4 x plus 3. Once it's in slope-intercept form, the coefficient of the x is the slope, and then the number that's off by itself is the y-intercept. Again, you can graph this if you want. But I'm just wanting you to here. We're just asked to identify the slope and the y-intercept, but you can see exactly what the slope is and what the y-intercept is if you graph it. For our number 12, we need to find the slope and the y-intercept, but again, it's not in slope-intercept form. Here, to get the y by itself, to put it in slope-intercept form, we just have to divide by 6. I want to reduce that negative 8/6. Because that is the slope, but you should always reduce your slope if you can. It's actually negative 4/3, and the y-intercept here is negative 3. For number 13, we are trying to find the average rate of change, but that's also the same thing as asking what the slope is. So I want to see how much money, like how much the money spent changed over time. So I'm going to do change in money over change in time. So I'm going to subtract my money values. I'm going to subtract my time values, which in this case is in years. So it's the change in money over change in time. Now I'm going to be careful with my units because that's not just a 595. That's a 595 billion. So when I reduce the 595 over 5, it's not just $119 per year. Since that billion is right there, it's actually $119 billion each year. So your rate of change is that right there. For number 14, I want to find the distance that the wheel moves in 20 rotations. So this is going to be since it varies directly, I can write the direct variation formula. So 56 feet, it goes 56 feet in 8 rotations. So that means that the distance is equal to some value k times the amount of rotations. I can also build a table, which I'll show you how to use later. But here I'm going to use a direct variation formula. If I want to solve for the k, I take the value of distance and divide it by the given value of rotations. I get a k value of 7. So that means distance is equal to 7 times how many rotations I have. 7 times 20 is 140, so that means it goes 140 feet every time if it rotates 20 rotations. So that's using the direct variation formula, but varying directly is the same as saying they're proportional. You could write a proportion to solve for these values right here. So here I'm going to write a proportion. I can write it this way, or I can write it the other way. Either way, if you cross multiply, you'll get a x value of 140. So it's helpful if you do a direct variation way. If you do it as a proportion, they're really the same method. Here I'm trying to find equations from a graph. So I'm given a graph, and I want to write the equation. The y-intercept is -1. The slope is you have to go up 1 and over 2 to get to the next point. So your equation in slope-intercept form is 1/2 x minus 1. For number 16, the y-intercept is 0. The slope is it goes down 1 over 1. So this equation is y equals -x. If you simplify it, you could write -1x plus 0, but you don't need to write that 1. You don't need to write that 0. Again, those are both in slope-intercept form. For number 17, I have to graph an equation. Always start by graphing the y-intercept when you're in slope-intercept form. So the y-intercept being -3. Then use the slope to find the next point. I go up 4 and over 1. And you can do that just once and connect a line between 2 points. But if you plot at least 3 points, it just makes it more likely that your line is going to be more straight. So I plotted 3 points. For number 18, The equation is in point slope form. So I'm going to write point slope form here, and I'm going to plot the point, which is actually not 2 comma 3, it's negative 2 comma negative 3 because of the negatives that are preloaded into point slope formula. So I'm going to plot that point right there. Then I'm going to use the slope to find a couple of the points going up 1 and over 2. And I like to do it more than once, just so the line's a little bit more straight. Just because I like those other 2 points were like a little too close together. So this just makes it a lot cleaner of a sketch if you plot at least 3 points. You can plot more than 3 points if you want, but I would say the minimum you'd want to plot is 3 points. That's a really nice line. You can write that equation. If you don't like using point slope form, you can rewrite this equation in slope intercept form by getting the y by itself and then solving these for the y-intercept. And so that's the equation right here. You'll notice that equation matches up with the graph also. Here we're asked to write an equation in point slope form. I'm writing the raw form, the template of point slope form, and I'm just going to fill everything in. The y coordinate is negative 2, so I write that in place of y1. The slope is negative 1/2, so I write that in place of m. The x coordinate, which is the x1, is 2, so I'll write that in place of x1. And then I just simplify. Instead of doing minus negative 2, I just put a plus there, and this is your equation in point slope form. If I want to write this one in point slope form, again, I like writing the template, so I know what to fill it into. Put the y coordinate in place of y1, put the x coordinate in place of x1, put the slope in place of the m. And since y minus 0 is just y, I don't need to really write that minus 0. So either two of those would be correct. Here I'm writing an equation that passes through a pair of points. I'm going to show you 2 ways to write it. I don't care which way you do it. You can use slope intercept form or you can use point slope form. First, either way, whichever one you use, you have to find the slope, because when you're given 2 points, you can easily find the slope through a line that passes through those 2 points by using the slope equation. And so the slope here is going to be negative 1. So I'm going to fill that in place of m. Now what I don't have is the y-intercept, the b. I can temporarily insert the x and y coordinates and use that to solve for b. So now you just get b by itself. B comes out to 2, and now instead of it just being y equals negative 1x plus b, which is unknown, it's y equals negative x plus 2. And you can put the 1 if you want. It's not necessary, but you can. If I want to use point slope form instead, maybe you prefer using point slope form, again, I'm going to put in place of the y coordinate, I'm going to put the y1, the negative 2, and in place of the x coordinate, I'm going to put the negative 4. The only advantage to this is you don't have to remember to take the y and the x and turn them back into a y and x, whereas in slope intercept form, you have to remember to rewrite them back as y and x. You can also do it in standard form, but standard form is just a rewrite sort of slope intercept form. So I would recommend using either slope intercept form or point slope form to solve these. This one I'm going to do the same thing. So I'm going to have to find the slope between those 2 points by subtracting the y's, subtracting the x's, and dividing those results. So when you take the difference of your y's, you get 15. The difference of your x's is 3. If you reduce that, you get either 5 over 1, or you could say just 5. Again, I'm going to write slope intercept form, but I only know my m. I don't know my y-intercept yet. I temporarily plug in the x and y coordinates, and I use that to solve for the b. And once I solve for that b, I take those x and y's that I substituted, I put them back as x and y, and I put them back into this equation. So you never just write a bunch of numbers as the equation. You have to write a y and an x somewhere in that equation, but you get y equals 5x if you write it in slope intercept form. You could write it in standard form too by just moving the x to be on the same side as the y, but again, I think just leaving it in slope intercept form is a good way to do it. If you like point slope form, the strategy is similar. You still have to substitute your slope. You still plug in your x and y values, and you just get an equation that looks a little different. You can plug in that point into the equation, or you can use the other point for point slope form. You could have also used that other point 2 comma 10 for the slope intercept, but you would have got the same answer. But point slope form equations are non-unique in that you can have many different ones that graph the same line. Here I want to look at two methods I can use to write the equation of a line given its graph. So I'm going to use 15 and 16 as examples. I've already written the equations in slope-intercept form. Now I'm going to write the equations in point-slope form. So I can use any of these points here that I circled, and I'm just choosing those points because they're nice whole number points. And that's the equation in point-slope form, which we've used that several times to solve the equations, many of the problems here. For number 16, I'm going to use this point here, which is the point 2 comma negative 2. And if you put that in point slope form, instead of getting y equals negative x, which is in slope intercept form, in point slope form, it's y plus 2 equals negative, negative in front of the quantity x minus 2. So those are the two main methods you want to use to use a graph, find the equation of a graph. Here we want to find the y-intercept of the graph and equation. These are the two ways to do that. You can either find where it hits the y-axis. So if it's in slope-intercept form, the y-intercept is just provided. It's right there. It's a number by itself. Let's say it's in point-slope form, or if it's in standard form. There, instead of just looking at the number that's by itself and not attached to x, you can substitute in place of x a value of 0 and then get the y by itself. And when you do that, you get the y-intercept. I'm going to graph these equations just to confirm that I'm doing that right. So you see if it's in slope-intercept form, y equals 2x plus 5, there you go. The intercept is 0, 5. The other equation, there you go. The y-intercept is 0, negative 10. I should have a negative 10 written right there, not a positive 10. So the y-intercept is negative 10 for that one, because negative 12 plus 2 is a positive 10. For this one, we want to look at if can we graph a line if its slope is undefined. We actually did this a little earlier when we calculated the slope of that line. It was x equals 6. But if you have a vertical line, it's going to have a slope that's undefined. And these are two examples of equations of vertical lines. The reason why it's undefined is because it has a rise. Like here, in between these 2 points is a rise of 3, but it has no run. It has a run of 0. So you're dividing by 0. If you divide by 0, you get undefined. Last one, 26. So we're working and we're earning $18 per hour, but we're getting a $75 bonus. Now the $75 bonus doesn't adjust with how many hours you work. It's just $75 only once. You only get that bonus once, but you get $18 per hour. So I'm going to graph as if I work 1 hour, 2 hours, 3 hours, so on and so forth. And I want to look at the graph of this thing, which is going to vary depending on how many hours I work. Now, if you work 0 hours, it wouldn't be really realistic that you get $75. Like, that wouldn't really make sense. So you can kind of ignore that point. I'm just going to start it at 1. If I work 18 hours, it's 18 times 1 plus 75. If I work 1 hour. If I work 2 hours, it's 18 times 2 plus 75. I can fill in those y values right here. I can calculate them by hand. I'll also show you how to do it in a calculator. But these are, here I'm just plotting those points onto the graph. And you could technically connect the points between those grounds. You could work like half an hour. So it does actually make sense to connect the points between the graphs. You don't have to keep it discrete. But there are my x and y values plotted on there. If you want to see how to use a calculator to assist you, you can use the table values right here. And here are the settings I use in my table to automatically generate those. That's in table set. But I find it just easier to even just do it by hand rather than relying on a calculator in this case. You can even look at the graph of the line, but the problem with relying on a calculator to graph, especially with big numbers like this, is that you have to have the right window. So I have to know something about my domain and range of my function to get the right window. So again, I suggest just providing a rough sketch of the graph is going to be sufficient. And you'll notice that when I set my window right, it looks just like it does. That's it for the study guide. Good luck.